Hello everyone. In the last lecture we discussed about analogous treatment, that is analogous to Rankine-Hugenoid treatment of shock waves. That last class was actually the treatment which was initially proposed by Davis, and that is, if you remember, that is that a piston in a cylinder compressing a compressible fluid. So now here we will discuss the actual the shock wave treatment, which is also known as the Rankine-Hugenoid treatment, that is the conservation equation of mass, momentum and energy. So as we know, the shock wave is has the characteristic of a steep wave front and also we know that no lateral flow, that means uniaxial strain. So this allows the buildup of very high pressure or high hydrostatic component of stress, So if this hydrostatic stress, if the hydrostatic stress is much higher than the dynamic yield strength, that is yield strength at higher strain rate, then the shear stress resistance will be 0, and that will denote the shear modulus mu will be equal to 0. So this is, so if it is uniaxial strain, that will develop a very high hydrostatic stress, and if is several order higher than the or we can call several factors higher than and the sigma yield at dynamic, that is sigma yd. So then the shear resistance will be 0, the resistance to shear, that means shear modulus will be equal to 0, mu will be equal to 0. So if we note down these basic assumptions of this treatment, whatever that is Rankine-Hugenoid treatment, the assumptions for the shock wave, as we know, is first one is a shock is a discontinuous surface, and has no apparent thickness. So this is very with very less thickness. So shear modulus mu is equal to 0. That means it behaves as a fluid. As we know that for fluid it cannot resist shear stress. So we can assume it as a fluid, and also we should understand that this is restricted to only higher pressures, and the body forces, that includes gravitational forces as well, and heat conduction, negligible, and there is no elastic plastic behavior, elastoplastic behavior, that means it will not show a elastic behavior at small load and then it will go to plastic behavior, and the material doesn't go doesn't undergo phase transformation, no phase transformation. So, the shock wave can produce phase transformation, but in this treatment we will assume that there will be no phase transformation and no elastoplastic behavior. And also a fundamental requirement of stress wave, the shock wave is fundamental requirement is velocity of the pulse will increase when the pressure will increase, that we already discussed related to that. So, velocity of the pulse u will increase when the pressure will increase with increasing pressure. So, let us assume a shock wave front. Let us say we will draw the shock wave front like this. Let us assume this is x and p. So, we can have a shock wave front, we can draw a shock wave front like this. So, this is the front, we call, just I am drawing it a thicker line and just to show the importance of this boundary. So, this is shock wave shock front, we can write, and let assume this front is moving forward with a velocity us, and the particle velocity behind the front, when you call behind, this means behind is this way, and we will, when we call ahead of the struck front, this will be this way, because the shock wave is traveling from left to right, and so particle velocity in this behind the front is up, and particle velocity ahead of the front is u naught. So, generally we will have the treatment for u naught equal to 0, that means a stationary ahead of the front. So, here we assume that this is particles moving, and here we will assume that particles stationary. So, that means u naught equal to 0. So, we have here the behind the shock front, we have the density rho and then pressure P and then energy, internal energy as E per unit mass, and in this the other side we will have density rho naught, P naught and E naught. So, because this is the initial one, that is why we write rho naught, P naught and E naught, and after the shock wave travels through this region, then this density and pressure will change. So, the particles are moving actually at the behind the front and also at the shock front. So, that is these values rho, P and E is defined at this behind and also at the shock front. We will have will assume that there is a center of reference at the shock front, and we will assume that the observer is at the shock front. So, basically let us say it is moving with the front. This is basically, as I told, we have written here Rankine-Hugenoid treatment. The Rankine-Hugenoid treatment is for Hugenoid treatment is originally developed this for fluids, as we know that for high pressure we assume that even for the other materials we are assuming it as a fluid. So, the displacement of the particle, that means we have behind the front UP and ahead of the front U naught, that displacement is responsible for the pressure build up due to the shock. And so, as we mentioned that the center of reference, the observer is here. So, that is why the apparent velocity behind the shock front, behind is US minus UP, and ahead of the shock front is US minus U naught. So, that means these apparent velocities are actually for the fluid moving. Suppose this is the shock front, so the fluid moving inside the shock front will have a velocity u naught, apparent velocity, because the center of reference, and we are assuming at the shock front. So, if you see from the shock front, if we are moving with the shock front, then the apparent velocity is US minus U naught of the fluid moving into the shock front. So, this is the shock front, and then the apparent velocity of the particles, let us say here also we can draw the particles. So, these particles go inside this to the shock front at a velocity US minus U naught, and the particles inside the shock front, I mean that means actually behind the shock front, will go away from the shock front at a velocity US minus UP. So, these are the apparent velocities. We will first start with conservation of mass, and then conservation of momentum and conservation of energy, like how we did for that the analogous treatment discussed in the last lecture. So, conservation of mass, again we are drawing the shock front. So, mass moving towards the front, this mass is A is the area of that cross section, A rho naught US minus U naught dt. We are assuming the time of travel is dt. So, that is basically, as you can understand, the area, or otherwise we can write it this way, rho naught first and then area. So, this will give us the volume multiplied by rho naught. So, which is the total is mass moving inside towards the front, and mass going away from the front is, we can write it as rho density multiplied by area A US UP dt. So that is, as you know, US minus UP, and or in this side on the right hand side US minus U naught, those are the apparent velocity we saw earlier. So now for conservation of mass we can write like rho naught A US minus U naught dt is equal to rho A US minus UP dt. So we can cancel dt and A from both the sides, and that will give us rho naught US U naught is equal to rho US minus U subscript P. And if we assume that this U naught is equal to 0, that means stationary material, actually stationary we call fluid, head of the front shock front. So then if it is U naught equal to 0, so this will give us rho naught US equal to rho US minus UP. So this relation will be important because we will use this relation in we will substitute these relations in other relations to get some interesting expressions. So after that we will try the conservation of momentum, that is, we know that momentum is mass multiplied by velocity, and which will be equal to the impulse. So momentum change will be rho A US minus UP dt. So this is the mass, and then multiplied by UP, the velocity, mass and the velocity minus rho naught A US U naught dt mass into the velocity U naught. So this basically, if you can see from the figure, so this is, one is ahead of the shock front and one is behind the shock front. So this difference in momentum will be equal to the impulse. That impulse will be F dt. So this F dt we can write it as pressure into area PA minus the P naught A dt. So that is the force PA by P naught multiplied by dt. So now if we try to simplify it with mass conservation, so what we can do is you can see here rho US minus UP. If we use this relation here, so that will give us A, we can already cancel it out. So what you can do is all A's we can cancel it out, and also dt we can cancel it out, dt. So now then we will use the mass conservation, the relation that will give us rho naught US UP. So if we use so we need to use this relation for conservation of mass, so that will give us rho us minus up equal to rho naught us minus u naught. So that will be this will be rho naught us minus u naught multiplied by up minus rho naught us minus u naught is equal to p minus p naught. So this will give us rho naught us minus u naught up minus u naught is equal to p minus p naught. So if u naught is equal to 0, the conservation of momentum relation will be equal to p minus p naught will be equal to rho naught us up. So this term rho naught us is known as shock impedance, like we got earlier sonic impedance. So and this is the relation of conservation of momentum for u naught equal to 0. And then we will come to the third conservation law, that is conservation of energy. So conservation of energy will give us, suppose the work done is equal to our total energy difference. So that means let us say internal energy and kinetic energy. Now the work done by pressure P minus the work done by pressure P naught, which we can write it as P A, the force into the distance of the travel by the particles, that is written as up dt. So minus P naught, the area will be same, the particle velocity will be u naught multiplied by time will give us the distance. So basically we can write f into x. So this is considering the original reference system. So we are not taking like apparent velocity or something. So then about the difference in total energy, which probably we can write it as delta k kinetic energy and delta E internal energy. So which will be look like the half of rho a us minus up, the apparent velocity of the particle moving away from the shock front, that is going to behind going towards the left side of the shock front. If you can draw again this shock front, so this way we are showing the kinetic energy, this is the m, and v square is up square. So sorry, what we wrote here is up should be in this direction, but the m is this correct. So m is this expression, and then the velocity of particle ahead of the shock front is u naught. So that we will see in a later. So this is the final kinetic energy plus our final internal energy, which will be internal energy per unit mass multiplied by the volume, multiplied by the mass. So, that will be like density rho A US E minus UP dt. So, this is also mass, and this is for final configuration, and then minus the initial one, which will be equal to half of rho naught A US minus u naught dt u naught square plus E naught A rho naught US minus u naught dt. So, this is initial, that means before the shock front travels to the material. So, this is the initial one, and then when the shock front travels, enters that area, and then that is the final one. So, now if we can simplify it, so what we can do is we can take u naught equal to 0, that we know that stationary particular stationary ahead of the shock front, that will give us, if we simplify it, basically so if we have this delta W delta K plus delta E, and that will give us P U P dt multiplied by A is equal to half of rho A US minus EP UP dt, the whole thing to the power UP square, or to write it like this, plus E A rho US minus UP dt, minus the third term will be 0, because that has an u naught square, u subscript naught square. So, and the fourth term will be E naught A rho naught US minus u naught will be, that u naught part will be 0, and dt. So, now we can cancel out the dt in every term, and also A, the area, in every term. So, finally this will look like this, half of rho US minus UP square plus E rho US minus UP minus u naught rho naught US. So, from conservation of mass, so we got that rho US minus UP is equal to rho naught US. So, if we substitute that, that will give us P U P, this part if we substitute, half rho naught US, that is the sonic shock impedance, and then UP square, plus we can simplify it more, rho naught US E minus E naught. So that is again we are simplifying this portion with the conservation of mass. So this is basically what we found is conservation of energy, conservation of energy. So what we found in our discussion here is that the first one is conservation of mass, that is, if we summarize it, the three conservation equation. So this is conservation of mass, and then second one is P minus P naught rho naught US UP, that is conservation of momentum, and third one is the conservation of energy. Half rho naught US UP square plus rho naught US E minus E naught, that is conservation of energy. And all of these are for as we know, the head of the shock front, the particle velocity, particles are stationary, E not equal to 0. So although this is we have written this conservation of energy as in this form, but there is another form of conservation of energy is more popular. So we will work on that, will derive that as well. And here we can see that we have 5 variables in these three equations. We have 5 variables. So those are P, UP, US, P is the pressure, UP is the particle velocity, US is the velocity of the shock wave front, and then another one is density of the fluid, and then E, the internal energy per unit mass. So let us see that. So we will require one more relation that you can understand from here. So we will discuss about that later, because we have 3 equations and we have 5 variables. So if we get one more relations, then what we can do is we can determine these parameters of shock wave parameters in terms of another one. So that we will discuss. And so before that, we want to see what is the other form of these energy equation, which is more common. So we will go a little quickly. So so if you see this this equation, so if you want to simplify, E minus E naught is equal to P UP rho naught US minus half of rho naught US UP square divided by rho naught US. From the conservation of momentum, what we got is conservation of momentum, we got UP equal to this conservation of momentum equation, we got that UP is equal to P minus P naught, divided by rho naught US. So if we substitute UP, and that will give us E minus E naught P minus P naught rho naught square US square minus half of P minus P naught square divided by rho naught square US square. Again, from the conservation of mass, we can substitute this So that will give us, we will do in the next. So from the conservation of mass, if we use it, we will get expression like this, which will be equal to minus rho up, and again if we use the conservation of momentum, that will, in this relation, that will give us something like this. So now if we combine this, we will get rho naught us square minus rho p minus p naught 1 divided by rho naught minus rho. So if we know that 1 by rho is equal to V, volume V, so in here if we do this substitution, sorry, this is P only, so P minus P naught 1 by V naught, 1 by V, and 1, that will give us 1 by V P minus P naught, will have V multiplied by V naught, V minus V naught. We can cancel V and V here. So this we can write, there will be one remaining V naught. So that will be, can be written as 1 by rho naught P minus P naught V minus V naught. So from here, I think what we can get is rho naught square us square is equal to P minus P naught V minus V naught. And if we substitute this relation in an earlier relation, that is earlier relation of conservation of energy, is equal to P minus P naught divided by rho naught us square minus half of P minus P naught whole square rho naught square us rho naught square us square. So the previous expression, if we substitute here, that means the previous expression what we got is rho naught us square equal to P minus P naught V minus V naught. Sorry, this is P minus P naught V naught minus V. If we substitute this, what we will get is P minus P naught multiplied by V naught minus V P minus P naught, and then minus half of P minus P naught square, and then V naught minus V P minus P naught. So this will be P. So this actually cancel out. So that will get P V naught minus V plus minus half of P minus P naught V naught minus V. V naught minus V, if we take it out as a common factor, so P minus half of P plus half of P naught, which will be equal to half of, so we will write first P plus P naught V naught minus V E minus E naught. So this is the more common form of energy. So as we have discussed, we had three equations, that is conservation of mass, conservation of momentum, and conservation of energy, and we had 5 variables 5 variables that we found as P, UP, US, density, and then E, and these 3 equations are mass, momentum, and energy conservation equation. So, if you want to know the relationship, let us say of these shock wave parameters, let us say we need a relation between Pu and US, or P and let us say UP. So, what we need to have one more equation so that we can express these parameters in terms of other parameter. So, there is another, the fourth the relationship, that is relationship we required is an empirical one, empirical that is experimentally determined, empirical one, that is we can have, that is a relationship between US and UP, shock wave velocity and particle velocity. So, US will be equal to C naught plus S1 UP plus S2 UP square plus dot dot dot. I mean, that means we can have more terms, and this equation is known as equation of state for a material on the shock wave. So, what is C naught? C naught is sound velocity at 0 pressure, and S1, S2 they are empirical parameters, Now, for most metals, we can assume S2 is equal to 0, and the higher the parameter will be 0, and that will give us a linear relationship between US and UP, which will be equal to S1 UP. So, this is the equation of state. This has a linear relation, and it is valid for material with which does not undergo phase transformation. So, no phase transformation. This is valid for no phase transformation, or no material porosity. So, if the material undergoes phase transformation under shock wave, or if the material has porosity, this linear relationship of US and E I mean, that means shock wave velocity and the particle velocity will not hold, and that will have we need to consider other relationship. So, this relationship of US and UP, which is C naught plus S1 UP, can be plotted. So, we have experimentally measured equation of state. We will write EOS curve. This is EOS, equation of state curve. So, this is x axis will be UP, which is let us say in kilometer per second, because these waves travel very fast, and then US, which is also in kilometer per second. So, if you keep like this, and then so this is 0.4, 0.8, 1.2, 1.6, 2.0, and here if we have 2, 4, 6, 8, 10. So, our curves will look something like this, let us say for iron or some other material. So, let us say this is for iron, or if you have some other material, let us say for copper, this can be little different. Maybe this is iron, the earlier one, and this may be copper. So, these will be straight lines, as you can see this intercept, you can see that C naught, and then slope is S1. So, these are the relations we can have from the equation of state, as we discussed. This is valid for no phase transformation and no material porosity, and also the equation, the earlier equation E minus E naught equal to half of P plus P naught V naught minus V. So, this equation actually establishes a relation between pressure and density, and that is immediately behind the shock wave. That means this is the shock wave, so it is traveling with US. So, in the behind the shock wave, what is the pressure and what is the density. So, this equation the earlier we derived from conservation of all the conservation equations. So, this will is the relationship is known as, this relationship between P and rho is called Rankine-Hugenoid relationship, and also, or it is called only Hugenoid. So, we will discuss the rest of part of it in the next lecture. So, what we discuss today is the Rankine-Hugenoid treatment for shock waves, and it consists of the three conservation equations: conservation of mass, conservation of momentum, and conservation of energy. And we also discussed about another relationship which has the relationship between US and UP, the shock wave velocity and particle velocity, which is an empirical relationship that can be linear, a straight line when there is no phase transformation under shock wave, or the material does not have any porosity. Otherwise, this relation can be non-linear. And also we discussed about the Rankine-Hugenoid equation. So, with that, so we will finish today's lecture, and so we will discuss the rest part of it in the next lecture. Thank you.